Hi guys, how's it going? I thought I'd try something a little bit different here for this video. I'm going to use the Zoom app on the computer and share my iPad with you on this topic. So it might be a little clumsy at times, so bear with me, please. This video will be about introducing the idea of conditional probability, and I actually really like the problem sets that I think I've mentioned a couple of times already. The problem sets on this topic in Chapter 7 are pretty good. But I think it'll really help a lot if I do a little bit of an introduction to those problems. So that's what I'm going to use the iPad for. All right. And so we'll do actually problem number 67 and 68 as a way of introducing this idea. And I'll leave you with kind of a sort of a basic formula that you can use. And so there will be there'll be that. There will also be the introduction of this new it's a way of modeling probability called a two-way table, and it looks like an area diagram, but it's a little bit different. And so you'll get some notation, a little bit more vocabulary, and like I said, a formula at the end of this to kind of help you get going on these problems. But mostly I'm just going to be talking about the first couple of problems, because I think with a little bit of help on getting started on those, you'll be able to kind of pick it up yourself. Okay, so conditional probability is a very important, very practical and useful aspect of probability calculations. So this is a good thing for you to get a handle on. Okay, I'm going to share here the iPad, and we're going to go straight into problem number 67 from Chapter 7 out of your textbook. All right, so let's see. Take a second here to get this going. All right, I'm going to share here the iPad. All right. Okay, great. So this is problem number 67. And I've pretty much copied the text here for this problem. It says Mary Bell is playing the board game called Eight the Hard Way with her friends. Each player rolls 2 dice on his turn and then moves according to the sum on the dice. However, if a player rolls 2 4s, which they call 8 the hard way, that player instantly wins the round and a new round is started. So one of the players, whose name is Delaney, is also playing. So Delaney steps into the kitchen to get snacks, and she hears, out of the room there, she hears Maribel shout, "Woohoo, I got an 8." So Delaney, back in the kitchen, knows that Maribel rolled a sum of 8. And then here's the question here. With your team, help Delaney investigate the probability that Maribel rolled 2 4s and won the round of play. In other words, calculate the conditional probability, all right, that Maribel rolled 2 4s, given that you know she rolled a sum of 8. All right, so I'm just going to pair, that's the main question there, and that is a classic sort of an example of a conditional probability question. Let me rephrase it for you there. They're asking the question, what is the probability that if we know Maribel rolled an 8, what is the probability that she got 2 4s to get that sum of 8? Because as you know, there's more than one way to get a sum of 8. And the first problem in the first part of the problem says, make a diagram to represent all the possible sums of numbers when rolling 2 dice. That's a little bit tedious, but here it is. Here's the table that shows all the possible things that can happen when you roll 2 dice and add up the numbers. In other words, this is the sample space right here. All right, this little chart. Okay, you can see there are 6 sides on each die, and therefore there are 36 possible sums. Some of them do repeat, however. And so the first question there is, what is the probability of getting an 8? Well, an 8, you can see in this table here, an 8 happens all of these different ways right there. It happens 8 different ways. All right, there's 8 different ways to get a sum of 8, and therefore since there are 36 total possibilities, there are 5. I hope I said 5. 5 out of 36 ways to get 8 out of rolling 2 dice. So the probability of an 8 is 5 out of 36. All right. The second question that they ask here, what is the probability of getting 2 4s? All right, well, 2 4s, there's only one way that that happens. That's right there. You get a 4 and a 4, and that's just, that's the only way you can get 2 4s is to get 2 4s. And so that's actually 1 out of 36. All right. Now, here's the conditional probability question. What is the probability then that she got 2 4s given that she rolled an 8? And this is the phrasing on all of these conditional probability questions. So this is the first clue that I want to sort of point out. Anytime you're asked a conditional probability question, you'll see that word given as part of the question, all right? So what's the probability that she rolled 2 4s given that she rolled an 8, all right? And so the condition in the conditional probability question here is this right here, is that she rolled an 8. So since there are 5 ways that she can get an 8, and only one of them is 2 4s, then the probability of getting 2 4s given that she got an 8 is 1 out of 5. All right, so think for a second there. Hopefully that makes sense. You can see that if she could get a sum of 8 in 5 different ways. One of those 5 different ways is 2 4s. So the conditional probability there, 2 4s given 8 is 1 out of 5. It's kind of saying the same thing, I know. Okay, the next question they give there in this problem, number 67, is something else, another conditional probability question. And when you see this, you can see how many possible conditional probability questions we could ask. So they're just giving you one more little chance here. What is the probability that she rolled an odd number given that she got 9 or more? There's a little bit more context for this question. Something about rolling high, meaning rolling 9 or greater, a sum of 9 or greater. And so given that, what's the probability that she rolled an odd number? All right, well, look at the odd numbers here. There's first off, there are 10 different possibilities that she could have gotten a rolling 9 or more. If you count up, there's 4 9s, there's 3 10s, 2 11s, and 1 12. So there's 10 possibilities. Well, how many of those are odd? Well, it's simple. 1, 2, 3, 4, 5, 6. You just count them. That's all there is to it. And so the answer to that conditional probability question is just 6 out of 10. Okay, so a couple of quick examples there of conditional probability. Now, what the next problem does is very important for us because it introduces this other probability model that I think you're going to really like once you sort of appreciate how well this sets things up for this kind of a question. All right, this is called a two-way table. Excuse me. And in this problem here, the question is about students at a high school, something called Einstein High School. It's not very many people at this school. And they've asked them a question: do you eat at the cafeteria, yes or no? And are you on the student council, yes or no? So they've asked those 2 questions of the population at this school, and these are the answers that they got. All right. And so this two-way table here is a really interesting way to break down some statistics like survey questions. And then you can generate probability questions and calculations in this table here. I'll just show you how. So they asked the question, it's called a two-way table basically for one reason here. You've got 2 sides, so it looks like an area model, but it's not. And it's, the 2 sides are basically broken into a yes or no question. So one question was, do you eat at the cafeteria? And the answers are either yes or no. There's no like, I eat at the cafeteria only if they serve pizza, or I only eat on Fridays with my friends, or nothing like that. It's either you do or you don't. And that's a characteristic of a two-way table. Each side of this table is basically a yes or no question. So that's a really important feature because you'll be asked to set up these two-way tables eventually. So you got to know that it's each side of the question, each side of the table is a yes or no question, right? And the other question that they asked was, are you on the student council? Well, that's clearly a yes or no question. So that one seems appropriate. So so these are the numbers that they got in this table here. all right? And one of the first questions that they ask is, what is the probability of being on the student council at this EHS? That's Einstein High School in their problem. You can see the problem, it's number 68. Um, so, so look at that. What is the probability of being on student council at this high school? Well, on student council, all right, how many of those are there? Well, there's 6 here, there's 34 here, so that makes a total of 40. So there are 40 people on the student council, but we need one more number to figure out what the probability is. So these really aren't probabilities in this two-way table. They're just raw numbers, you might say. We need to know how many students are at this school, right? So, so let's do a little bit of work here first. There's 40 people that are on the student council, and if you count up the people who are not on student council, that makes 30 plus 170, that's 200. So 200 students are not on student council and 40 students are. Well, that makes 240 students, all right, total at this school. Let's check that with the cafeteria question numbers, all right? So there are 36 people who say that they do eat at the cafeteria, and 170 plus 34 is 204 students who say they do not eat at the cafeteria. And if you add those two numbers together, you also get 240. So that checks out, all right? 200 plus 40 and 36 plus 204, you get the same total. So we know that there are 240 students at this school. So now to the question of what is the probability of being a student on student council? Well, all you have to do is take the yes questions, which is this right here, the 40 people said yes, they are on student council, and out of 240, so that's our probability. It's 40 out of 240, and just to be nice, we'll reduce that down to 1 out of 6. So it's a 1 out of 6 chance that a student at this school is on the student council. All right, so let's move on because we want to get to a conditional probability question, but we kind of have to answer some of these basic questions first. So it says, copy the table and shade the cells with the students who eat at the cafeteria. All right, so let's get out the highlight tool here and shade in the people who said, yes, I do eat at the cafeteria. So that's all of these people right there. All right, there's 36 of them. What is the conditional probability, all right, of a student being on student council given that you know the student eats at the cafeteria? Okay, so the condition is that the student eats at the cafeteria, all right? And the question is, what is the probability of being on student council? So that's a yes on student council, given that you know the student eats at the cafeteria. Well, look at this. There are 36 people total who eat at the cafeteria. That's our condition. We're saying out of those 36, how many of them are on student council? Well, it looks like there are 6 of them. All right. So that probability is a pretty easy one to figure out. It's just 6 out of 36. Okay. And that also reduces down to 1 out of 6. Okay. So we happen to get the same probability there. The probability of a student being on student council is 1 out of 6. And then the second question is, the probability of a student being on student council given that they eat at the cafeteria is also 1 out of 6. All right. So those two things happen to be the same. They're not always the same, but this one, they happen to be the same. And here they're going to address that sort of coincidence here by giving you a definition. 2 events, A and B, are called independent if knowing that event B occurred does not change the probability of event A occurring. Now, this is a tricky and it's kind of a slippery topic. It seems very easy to grasp at first, the idea of what are independent events. And we got to back up and unpack this word a little bit because there's more there than meets the eye at first. When you first talk about independent events, their definition right here is specific to conditional probability in this problem, but there's kind of a more broad and simpler definition of independent events. 2 events are independent if they don't influence each other. That's kind of a simple definition of independent events. For example, if you flip a coin and the probability of getting a tails on that flip is 1/2. If you flip that same coin again, the probability is still 1/2. And if you keep flipping the coin, the probability doesn't change. Every single flip is independent of every other flip. So one flip's result doesn't influence the results of another event. That's kind of a simplistic, actually, example of what independent events are. And if you look it up on the internet, that's most likely what they're going to tell you. It's a more complicated and nuanced definition here when we're talking about conditional probability, however. So two events are A and B are independent if knowing that event B occurred does not change the probability of event A occurring. So now we're going to talk about them in the context of conditional probability. These two events, A and B, are independent if the probability of A given B equals the probability of A. So in other words, the probability of A is what it is. If you set up the condition that B happened first, and it doesn't change the probability of A, then that's kind of a mathematical way to arrive at the idea that the events are in fact independent, okay? So in other words, if the probability of A given B and the probability of A are the same number, then the events A and B are actually independent, all right? So now they ask this question, are the events being on student council and eats at the cafeteria independent? Well, when we look at the first one, are the events being the probability of being on student council, we did that right here in part A, all right? And that was 1 out of 6. The next question we answered was, what is the conditional probability that given that the student is at the cafeteria or eats at the cafeteria, what is the probability of them being on student council? We also got 1/6. And so yes, the events are independent because the probability of, let's see, I guess this is a little tedious to write out here, so bear with me, but the probability of being on student council given eating at the cafeteria, I'm going to sort of shorten the word here, equals the probability of being on student council. All right. In other words, it fits this definition perfectly. If the probability of A given B equals the probability of A, so here's A and here's our condition B, and it equals the probability of A. All right. So this rule fits for this situation. Okay. In other words, the events being on student council and eating at the cafeteria are in fact independent events. They don't change each other. Okay. Part D of this problem introduces yet another little phrase for you, the phrase mutually exclusive. All right. And fortunately in math, that in the math context, that means exactly the same thing that it means just in a general language sense. Two events are mutually exclusive or disjoint if they cannot both occur at the same time. That is, two events are mutually exclusive if probability of A and B equals 0. Okay, and I'm going to answer this question. Are the events on student council and eats at the cafeteria mutually exclusive? No, they are not. Let's go back up and look at the two-way table to see why. All right, and here's another dive into what a two-way table actually is. That's a really important feature of this question here. So this is a two-way table. I said it's got kind of a yes or no question on each side. But the other thing that's really important to keep in mind about these two-way tables is that these numbers here in the table itself, this number 30 and 170, all these numbers here are all kind of A and B type questions, all right? So the and part of that kind of calculation right there, that's a built-in feature of a two-way table. Every number in a cell in one of these two-way tables is an and kind of thing. So this 30 is the probability, is the number of people that eat at the cafeteria and are not on student council, something like that. So in other words, if we called student council being event A and being eating at the cafeteria event B, this 30 here in this first cell represents the number of people who you might say are not A and B. The 170 and the one next to it is not A and not B. All right, down here in this cell down here, yes and yes. This is in the lower left box, A and B. All right, these are not probabilities. Once again, these are just raw numbers, but they are the combination of the two events happening at the same time, or the negation of those, like A and not B is a negation of B. So that's what these numbers are. Okay, so let's go back to that question right down here. The probability of A and B equals 0 is a way to determine whether or not two events are mutually exclusive. So student council, eating at the cafeteria, can that happen at the same time? And when you look back up at the table there, yes and yes. All right, there is a value. It does exist that somebody could be on the student council and eating at the cafeteria. Therefore, these are not mutually exclusive events. All right, and just to be kind of short here, well, let's see. And we would say no, because the probability of student council and eating at the cafeteria, all right, which I'm being a shorthand right there, does not equal 0. All right, if it does not equal 0, then the events are not mutually exclusive. Okay, so that's a longish treatment there of this of these two problems. Here's the formula that I want to leave you with today in general, hopefully to get you started on this first assignment. This is just kind of a general formula for calculating a conditional probability. The probability of A given B is always equal to the probability of A and B divided by the probability of B. All right, so kind of keep this formula handy. It's a good way to kind of organize your numbers when it gets confusing, because it will get confusing. Probability, it takes so many words to describe something with probability that it's hard to kind of put things in little boxes to kind of keep them straight mathematically and be clear about the mathematical relationships, okay? One note here that I wanted to mention: if you do your own research on the internet or YouTube videos or something else about this topic, you're going to see this symbol right here, this A with a line and then B. It means the same thing as this, all right? So a lot of textbooks and a lot of math material uses this notation to indicate conditional probability, okay? Okay, I'm going to stop sharing the screen here. You can obviously watch this as many times as you want, or as you can stand, and we'll go back to my lovely face. Okay, so I'm going to post this video and the assignment here, and you'll be able to take advantage of both. All right, starting off with our topics on conditional probability. All right, leave me a question in the forum if anything I said in there was confusing. You know, we'll start off. Check out the forum as usual, and we'll see you in class next week. Okay, bye.